How you doing, Year 10s, and welcome to another video. This is topic 1.4, what is the structure of an atom? We go inside atoms, we look at writing them, and then we talk about electron configurations. Let's go. Alright, topic 1.4, we talk about what makes up atoms, we look at writing them with a symbol convention, and then we look at electron configurations. There's a number of different learning intentions for this video, so please make sure that you go through. Now, there's a number of learning outcomes for this video, so make sure you go through them, have a read of them, know what we're going to do. This is probably the hardest video we've done so far. Have a read of them, and then let's get into it. Alright, so the center of the atom is called the nucleus. It contains two subatomic particles, the protons, which are positively charged, and the neutrons, which have no charge. Electrons are the subatomic particle that orbit the nucleus in fixed regions that we call shells. So in the nucleus, the dense center of the atom, we have the protons, and we have the neutrons. The protons with a positive charge, the neutrons with no charge. The electrons can be found orbiting the nucleus in these fixed regions that we call shells. So the three different particles, the protons, the neutrons, the electrons. The protons and the neutrons are sometimes called nucleons because they can both be found in the nucleus. The electrons, they can only be found in the shells. Now the charge on a proton is +1. The charge on a neutron is 0, and the charge on an electron is the exact opposite of a proton, which is -1. The weight of a proton is said to be 1, the weight of a neutron is also said to be 1, and the weight of an electron is given the value 0, but that's not really true because it does weigh a bit. It's just so tiny that we pretend that it weighs nothing. If we're asked to write atoms according to their symbol convention, we need to apply these simple little rules. We have A, which is the mass number, which tells us the number of protons and the number of neutrons. We have Z, which is the atomic number, the number of protons, and then we have the symbol, in this case X or C for carbon. So the definition of the mass number is the number of protons plus the number of neutrons, and we simply add those together, and that goes in the top left hand corner. The definition of the atomic number is the number of protons, and that's the bold number found on the periodic table. That's what makes every atom different, the number of protons. So if we have the example below where we have 23592U, what is that element? Well, that's uranium. The number of protons, well, every uranium element will have the same number of protons, which is 92. To work out the number of neutrons, though, we would need to get the mass number, which is the number in the top left, and take that away from the number of protons, which gives us 143. So 143 neutrons. The formula for that would be A, take away Z, which equals the number of neutrons. So atoms that are the same always have the same number of protons, but they might have a different number of neutrons. Atoms with the same number of protons but a different number of neutrons are called isotopes. So the definition of an isotope is an atom with the same number of protons but a different number of neutrons. So for example, technetium, which is element number 43, it has some interesting chemistry because it's used in medical imaging. Now, if you have a look on the periodic table, the atomic number is 43, and then the mass is this 98 with its inside brackets. Now, if anything is inside brackets on the periodic table, it means that it's radioactive and unstable, and it will start to decay and break down until it becomes stable. Technetium has three common isotopes, technetium-97, technetium-98, and technetium-99. And if we're asked to write those according to the convention, we would place the mass number in the top left and the atomic number in the bottom left. The difference between all of these three will be 1 or 2 neutrons. They all have the same atomic number because they are the same element. They're all technetium, so that doesn't change. Any atom that has the same number of protons as another one is the same atom. The only thing they differ by would be neutrons. That makes them isotopes. Now we'll be asked to fill the electron shells by working out the electron configuration. And these electrons, they fill in a very specific order. Certain shells can only hold certain numbers of electrons. So the first shell can only hold 2 electrons. The second shell can hold 8 electrons. The third shell can hold 18. And the fourth shell can hold 32. Now these fill up in terms of energy. The first shell is the least amount of energy. Oh yeah, and if we were looking at the nth shell, it would be 2n squared. That's the rule. So the first shell, that has the lowest energy, so that fills first. And the rules, they basically follow energy levels. So we have to fill shells with the lowest energy first. Now to do this, we start to use pairs. We start to group electrons in pairs, and for the reasons that you'll find out in year 11. But let's start with beryllium. Beryllium has an atomic number of 4, which means it has 4 protons and 4 electrons. So we've got to draw a diagram showing how those 4 electrons are filled. So in the nucleus, we can just write 4p to say it has 4 protons. And now, because beryllium has 4 electrons, that means the first shell will be full. So it has 2 electrons in the first shell. They're paired up. In the second shell shell can hold 8, but we only need 2. So we put them separately because the electrons don't want to be paired until they're forced to be paired. So for the next one, we have neon. Neon has 10 electrons, which means it also has 10 protons. So we have 10p in the middle. The first shell can hold 2 electrons. The second shell can hold 8 electrons. So we will have a full second shell. So there are our 2 protons for neon. And now we go around filling them individually first. And then we start to pair them up so that they're all paired. We only pair them when they're forced to be paired. So those electrons are now complete. It has 10 electrons and neon has a full outer shell, which in the last video we talked about it being a noble gas because it had 8 electrons in the outer shell, and here you can see that. Potassium with 19 electrons is a much bigger atom and it's a lot harder to draw, and I do apologize if my circles get a bit cramped. So in the first shell, potassium will have 2 electrons. That means we've got 17 left to fill. In the second shell, well, the second shell can hold 8. That one will be full as well. So we'll put in our 8 electrons into the second shell. We've now accounted for 10 electrons. We need 9 more. Well, the third shell, it can actually hold 18 electrons. So maybe I can just stick the 9 in here. But that's not exactly how it works. I can never have more than 8 electrons in my outer shell. So I put in my 8 electrons, and then to make this stable, I have to have another shell. So potassium will have 1 electron in its outer shell, in the 4th shell, the highest energy level. The reason for that is I can never have more than 8 electrons in the outer shell. If we were asked to write their configurations, beryllium would be 2, 2, neon would be 2, 8, and potassium is 2, 8, 1. So here you can see that in the third shell, the third number, it only has 8 electrons in it. I can't put a 9 there. The electron configuration is not 2, 8, 9 because that would make it unstable. So we have to put that 1 electron in the 4th shell. We'll talk about the rules of how you can add more electrons in on the next slide. So after we get to calcium, we start to have elements that have moved into the transition metals. Now the third shell, it can hold 18 electrons, so having only 8 in it means it's not full. Once we put 2 electrons in the 4th shell, we're then able to put in the remaining 10 electrons into the 3rd shell. Those 10 electrons belong to the transition metals. So the important rule here is the valence shell, the outer electron shell, can never hold more than 8 electrons. If we need it to have more than 8, we have to put 2 electrons into the 4th shell before we can fill up the rest of the 3rd shell. So for example, vanadium is a transition metal that has 23 electrons. So what we do here is we fill up our shells, starting with our first shell, which can hold 2, our second shell, which can hold 8, Now our third shell, I'm just going to leave that blank and put 2 electrons in the fourth shell. Now that allows me to put more than 8 electrons in the third shell, and if I have a look, I just have to do a takeaway now, and I can work out that I actually need 11 electrons in vanadium's third shell. So if 11 electrons would mean it's a transition metal. Any element with more than 8 electrons in the third shell will be found in the transition elements. Nickel has 28 electrons, so I apply the same rule. I do 2, I do my 8, and then I leave a gap and put 2 electrons in my fourth shell. How many electrons am I missing? I'm missing 16, so that means the electron configuration must be 2, 8, 16, 2. Iron has 26 electrons, so we apply the same idea, 2 in the first, 8 in the second, leave the third blank, and place 2 in the fourth, leaving me with 14 electrons in the third shell. You won't be asked to draw any of these ones, they're too big and they get a little bit messy. Remember the rule, if I want to put more than 8 electrons in the third shell, I have to have 2 electrons in the fourth, which is why I was writing the line and then working sort of backwards to work out how many electrons are in that third shell. I can't do this, so this would be a bad example and why it doesn't work. For vanadium, I can't write 2, 8, 13 because the 13 means it has more than 8 electrons in the outer shell, which means it would be unstable. So that's the reason why I have to put the 2 electrons in the fourth shell first. Alright, topic 1.4, some top tips. Remember that the outer shell cannot have more than 8 electrons in it, so if you've got a transition metal, leave the gap and work it out after. Thanks for watching guys, don't forget, drop a like on the video, subscribe for more, and I'll see you next time.